Welcome to Decoding Complexities. I'm Pradeep. How does a computer understand the word king is related to man in the same way that queen is related to woman? How can it possibly grasp this abstract concept of royalty and gender? Computers don't understand meaning, they only understand numbers and structure. To solve this, we have to represent our data, whether it's words, images, or user profiles, not as isolated items, but as points on a map, a special kind of mathematical map with a strict set of rules. This map is called a vector space, and today we are going to build one from first principles. Before we can build a vector space, we need to understand its most fundamental building block, a group. A group is one of the simplest, most elegant structures in all of mathematics. A group consists of two things, a set of elements and a single operation that combines them. To qualify as a group, this combination must follow four strict rules. The first one is closure. If you take any two elements from the set and apply the operation, the result is still in the set. An integer plus integer is always an integer. The set is closed under the operation. And the second, associativity. It doesn't matter how you group the operations, the result is the same. The order of operations is predictable. And the third, the identity element. There must be a special do-nothing element. For integers and addition, this is the number 0. Addition 0 doesn't change anything. And the fourth, the inverse element. For every element in the set, there must be a corresponding undo element that gets you back to the identity. For 7, the inverse is -7. As a developer, think of these four axioms as an interface or a contract. Any set and operation that implements this group interface guarantees that the system is self-contained and reversible. It's a predictable and well-behaved system. Keep this in mind. We have our group contract. Now, let's build our vector space. A vector space is a more complex structure. It's a collection of vectors that can be combined and scaled. A vector space is defined by 10 rules. This sounds intimidating, but they are very logical. We can group them. The first 5 rules simply state that the vectors and the operations of vector addition must form a group. The first one is closure. For example, if we add two vectors v and w, the result is still in the same vector space v. The second one is the associativity. If you take an example of 3 vectors u, v and w, adding two vectors u and v and then adding the resultant vector with w should be equal to adding u with the resultant vector of sum of v and w. And the third one is identity element. There is a 0 vector such that adding this 0 vector to any vector will result in the same vector. And the fourth one is inverse element. For every vector v, there is a vector -v such that v plus -v will result in 0. And the fifth one is commutativity. The order in which we add the vectors shouldn't matter. For example, v plus w should be equal to w plus v. If the group follows commutativity, then we call this group an abelian group. Think of our familiar 2D plane. If you add any two vectors, the result is still a vector in that same plane. It follows all the rules of a group. The next 5 rules define how the scalars interact with the vectors. The first one is the closure and scalar multiplication. Multiplying vector v with any scalar should be present in the same vector space v. There are 2 different rules in distributivity. The first among these is multiplying a scalar with the addition of 2 vectors should be equal to multiplying a scalar with these vectors individually and then summing them up. And second one is adding 2 scalars together and then multiplying it with a vector should be equal to multiplying these vectors with scalars separately and then adding them together. And the next rule is associativity. The result from multiplying a vector with a scalar and then with another scalar should be equal to multiplying a vector with the product of these 2 scalars. And the final rule is the scalar identity element. For example, multiplying a vector v with a scalar 1 should result in the same vector v. This is the key. A vector space is a playground for our data. The vectors are the locations or objects in the playground. The rules guarantee that we can navigate this playground in a predictable way. We can add vectors to move from one point to the another. we can scale them to make them longer or shorter, all without ever leaving the playground. One final powerful concept here is a subspace. A subspace is simply a vector space that lives inside another large vector space. For a set to be a subspace, it only needs to satisfy two of the main rules. It inherits the rest from its parent space. The two critical rules are closure under addition and closure under scalar multiplication. Think of a 3D video game world. That's our vector space. The flat ground plane is a subspace. Why is that? If you take any two vectors on the ground and add them together, the result is still a vector on the ground. It's closed under addition. If you take any vector on the ground and scale them, it still lies on the ground. It's a closed under scalar multiplication. But a sphere in this world is not a subspace. If you add two vectors on the point to the surface of the sphere, the resulting vector will likely point somewhere outside the sphere. It's not closed. So let's go back to our original problem. How does a computer solve king is a man or woman? It's because a model like Word2Vec learns to place every single word as a vector in a high-dimensional vector space. This space is designed to follow all the rules we just defined. The model learns that the vector from man to woman represents the concept of gender. It also learns that the vector from man to king represents a concept of royalty. Because this is a true vector space, we can do math. We can start at the vector is king, subtract the man vector, and add the woman vector. The resulting point in this space is incredibly close to the vector for queen. This is not magic. It is vector arithmetic. And it's only possible because our data is living in a playground with a strict, reliable set of rules. So, from the simple rule of a group, we build the framework of a vector space, the playground where our data lives. Understanding this structure is the key to unlocking why so many machine learning techniques actually work. If this detailed breakdown was valuable, a like is appreciated. Subscribe for more deep dives into the mathematics of machine learning. In the next video, we will explore the concept of linear independence. Thank you for watching.